Thanks for your time today. I'm Randy Holland, Marketing Director and Product Specialist for Safety Cover Enclosures. There is a shift in the status quo underway around containment backflow preventer installation. It's happening because of casualty losses and the influence of expert opinion. The forces behind this disruption are pretty strong. Now, we've always had great interest in safe drinking water, of course, but when you add to that access issues related to testing and maintenance, contingency costs related to retrofitting devices that become non-compliant, and at least two liability cost categories for designers, we're seeing that a tipping point has been reached. And with it, municipalities are actually rolling up their sleeves to write new laws. Backflow preventer installation probably isn't the most riveting topic for astronauts and nuclear physicists, but it's pretty important to mechanical and civil engineers. So as we proceed through this information, consider these questions in your mind. What's in it for me, the designer, to specify anything but the highest level of protection against contamination? And secondly, does having backflow prevention within my scope minimize the risk for all parties? And just so you know, this is not merely a theoretical discussion. Rest assured that we'll be talking about your neighborhood. You'll leave here with important information about any changing guidelines underway, known to be emerging in the 6 fastest growing areas of Central Ohio. So today we'll cover Cross-Connection Control Backflow 101. It's a quick overview of cross-connection control, what backflow is, why that's bad, and what the waterworks industry has done in the effort to neutralize its risk. We'll take a short look at how they work. Then we'll look at design and placement issues in light of this new information about public safety and the risks associated with both casualty loss and professional liability. We'll review some key ordinance changes around the country that foretell with some clarity where things are headed. And then, as promised, we'll look at cross-connection control ordinance changes in Central Ohio that affect you as a designer. So why do we need a cross-connection control program at all? Well, that's easy. Safe drinking water. But how does backflow prevention protect drinking water? I think my ancient art illustrates that point perfectly. Our friend has attached a pressurized sprayer to his garden hose spigot. And because the pressure in that sprayer has overcome the ambient pressure in his home's water line, some of that sprayer's chemicals are now flowing back into the city's water supply at the street. At the same time, his neighbor draws a glass of water from her tap, giving new meaning to the word firewater. Backflow happens when either or both of two events occur. The example shown here and in the previous illustration is back pressure. It happens when there is a higher pressure at the property or downstream piping than in the city or supply piping. It allows downstream substances to be pushed back into the city supply. Pumps, thermal expansion, even elevation are among the most common causes. The other event that causes backflow is back siphon. This happens when there is a negative pressure in the city piping, forcing the water that's been delivered to be reversed out of there. It reverses direction and gets pulled back into the city water supply. The typical cause is, of course, a water main break, but even higher than usual withdrawal rates can cause it, such as a flowing fire hydrant. You, as a designer, may specify one of two types of backflow preventer generally: the double check valve assembly or the reduced pressure zone valve assembly. As the subtext indicates, the difference between the two devices is perceived hazard. But how do you determine hazard? Well, that's a good question. And the simple answer is that the purveyor determines it, but most every jurisdiction is different. Every city has its own list of named examples of what constitutes the hazard threshold. But they all stipulate that if the anticipated use as you know it is not named explicitly, then they reserve the right to make the decision during code's review. It's important to understand that you cannot, as a designer, overprotect the incoming water service, meaning there is no penalty for providing the higher degree of protection. So you should ask yourself, is there wisdom at all of providing the lower level of risk protection? So let's have a quick look at how these things work. The double check assembly was developed in the 50s, and for what it does well. Anytime pressure on the downstream side exceeds pressure on the supply or public side, the valves close and the water stops flowing backwards. Keep in mind that no remedy exists in the event of a malfunction of the valve closure, or if debris in the line causes the valves to not close completely. Before we move on to the RP, I want to just cover the detector assembly. The detector assembly can apply to either one of the backflow preventers we're talking about today, either the double check or the RPZ. The difference in the detector assembly is it essentially consists of a bypass assembly that piggybacks the primary backflow preventer with a meter in order to detect any unauthorized use of water and or leaks on the system. Now, mind you, it doesn't provide an accurate measure of water flow since it's such a smaller diameter device, and as it exists in reality. You can see that it's a much smaller set of pipes that come across that double check assembly, and the meter piggybacks right over the top of it. The purpose is not to necessarily measure the flow, but to simply indicate flow and to detect leaks. The reduced pressure zone assembly consists of two independently operating check valves, just like the double check, plus a hydraulically operated differential relief valve located below the first check valve. This hydraulic valve and its placement make the RPZ virtually fail-safe. It's really quite elegant, but it does come at a cost to the area around the device. When a back siphon occurs, both check valves close. At that moment, the relief valve will open every time and evacuate the water between the valves. Now, some think that that event defines the limit of what water can ever flow into a drain, but boy, that's just not so. Consider a flow stop situation, one that might naturally occur at the end of a workday. If you look closely, you can see that a small pebble has lodged in the number 2 check valve. Because the number 2 check valve is not closing, all the water that has been delivered to the building will continue to flow back out of the relief valve until the private lines are cleared. And if this is a 4-story building, that's a lot of water. Now let's consider a full failure of the number 2 check valve, one that might occur if the device is knocked out of round or just a mechanical failure. It's essentially the same event with the exception that due to the larger valve opening, there is actually a higher flood rate. Now you have water flowing through the relief valve at full head pressure. Again, if this is a large or multi-story building, that is a lot of water very fast. Finally, consider a failure of both check valves. As long as there is no back pressure or back siphon occurring, water will be delivered normally. But any back pressure event will flow the delivered water to the relief valve at head pressure again and again. No water will escape back to the street because of the placement of the relief valve. Now, the main thing to take away from this is that both valves, the double check and the RPZ, perform the same function when they're operating properly. But only the RPZ is designed to use universal forces, specifically gravity and water pressure, to dispose of any backwards flowing water, even if the device fails. And by the way, they do fail. This picture was tweeted this summer by a Nashville backflow tester. It reads, "This is why we do it. A tiny pebble can render them useless. We test them right." There are 3 options for backflow preventer placement, and all 3 are widely practiced. First, inside a subterranean vault. This would have to be considered the legacy method still widely practiced among designers today, but as you know, an RPZ can never be installed below grade. And beyond the issue of being unsuitable for RPs, there are other compelling reasons to discontinue the use of vaults altogether. So let's look at the considerations: safety, liability, and changing demands. We've all seen the extraordinary measures OSHA imposes to legally access vaults for maintenance tasks. Fresh air exchange hoses, tents, extra men. The costs are more and more prohibitive, but frankly, the risk of serious injury is real as well. But beyond the costs of safety for on-site workers, liability issues persist. When a vault floods like this one, the mandatory test cocks are submerged, and in that event, a violation of the International Plumbing Code has likely already occurred. The water may look clean, but consider what would typically make up the constituents of that water. Runoff of lawn chemicals alone make this a clear and present danger to the water supply. In fact, it led the USC Foundation of Cross-Connection and Hydraulic Research in 2005 to change their recommendation of even double-check backflow preventer installations in vaults. They said the Foundation's recommendation would be to install the double-check valve above grade. Finally, changing demands. As a designer, you're obviously preoccupied with new construction. But buildings, through their normal life of changing tenants over time, change uses with respect to hazard levels. And hazard levels, or more precisely, the named hazard threshold, has become a moving target. Around the corner from our office in Nashville, I snapped this picture. It sits in front of a warehouse owned by an automotive dealer. When they bought the property and erected the building, they put a double-check backflow preventer down in that vault with the meter. A few years later, the city changed an ordinance that redefined their particular use as high hazard. When they sought a permit to upgrade their HVAC system, the city forced them to change to an RPZ. After constructing this huge vault, they now leave it almost empty with an RPZ in an enclosure perched on top. They easily paid 3 times for a single solution. Now this enclosure, if you can call it that, it really belongs in the Hall of Shame, doesn't it? It is safe to assume that the original designer didn't call for such a ridiculous setup, but nevertheless, if you were the civil on this job, you'd still feel pretty bad when you drove by it. In the foreground, you can see a common vault hatch. No doubt there was at some previous time a double-check backflow preventer down in that vault with the meter. But something changed. It might have been a tenant whose defined use constituted a higher hazard than the original user, and it might have been a change in the surveyor's threshold of what constitutes high hazard. But all these scenarios are becoming commonplace. By the way, this beautiful enclosure, whose height is unfortunately insufficient to cover those OS and Y valves, is actually a fiberglass shower stall turned on its side. What are you going to do? What about inside a building? If the double check is commonly installed in a vault, then equally common is that the RPZ is installed in an indoor location. Let's look at the concerns for the designer. Accessibility continues to be a concern, but more and more, ample room for testing and maintenance is being allocated. Now, it's certainly appropriate to list it as a concern, but believe it or not, there is a much more important issue. The main concern is property damage liability due to flooding. Here's what the American Society of Plumbing Engineers published in their 2006 design handbook. Before an RPZ is located, consideration should be given to both how much water will be discharged and where it will drain. Consideration must be given to the drain system to assure the drainage system can handle the load. If a drain is not capable of accepting the flow, other choices as to the location of the valve, such as outside in a heated enclosure, should be made. As we've illustrated then, an RPZ, behaving as designed, dumps water. This flood occurred in a Nashville hospital mechanical room and caused over $1 million in damage. What you're looking at is 2 sides of one wall. On the left, you see that the sudden water volume discharged from that Wilkins RPZ there with a floor drain right next to it moved the wall probably 18 inches into the next room, which happened to be a telephone and low voltage wiring room. Now, the insurer sought recovery from all the usual suspects, including the engineer, the architect, the contractor, the subcontractor, and even the most recent recorded tester, who, by the way, was the only one exonerated for sure because he showed up and was able to show documentation that he had been there to test the device and had done so in an appropriate time interval, and when he was there, the device worked properly. Now, while the details of who paid what were not made public, we do know that the property insurer was made whole by one or more of those remaining defendants. So if these things are designed to dump water, then Drain capacity is the issue, right? The chart on the left is from the Wilkins Corporation. It's the relief valve discharge rate chart for its top-of-the-line RPZ, the 375. It illustrates the flow rate of that device in various sizes and at various pressures. Note that a 2.5-inch device will flow 375 gallons per minute at 85 psi. And if you remember your fluid volume tables, and I'm sure you all do, you'll recall that a 4-inch drain pipe with a 6-inch fall per 100 horizontal feet evacuates clean water at a rate of 93 gallons per minute. If that device is flowing at 375 gallons per minute and you're only clearing 93, then you are flooding at a rate of 282 gallons per minute. The chart on the right is a drain requirements chart created by the city of Roswell, Georgia. Its importance really can't be overstated because it reveals that unless you intend to use 8-inch drain pipes at a 6-inch per 100 horizontal feet fall rate all the way to the sewer, you cannot justify anything larger than a 2.5-inch RPZ inside, and even that will require a 6-inch drain pipe. An article published this summer in the Chicago chapter of the American Society of Plumbing Engineers, written by David DeBoard, a former president of that organization, and now is actually a member of the National Governance Committee. He states all these facts better than I can. Now, he uses the manufacturer's data supplied by the Watts Corporation, and he uses 65 psi as an ambient pressure instead of my 85, but he actually does the math in the article and offers what he calls flood rates of 219 gallons per minute for the 2.5-inch and 3-inch models, and a flood rate, now this meaning after net of the drainage, of 482 gallons per minute for 4 inches and above. He concludes that regarding indoor RPZs, the floor drain capacity for RPZs of 3-inch diameter and higher are likely to be cost prohibitive due to necessary pipe diameter and fall rates. So we've covered subterranean vaults and inside the building. Now let's look at above ground in an enclosure. Let's take a look at the considerations: freeze protection, strength, drainage capacity, accessibility, and security. In 1996, the American Society of Sanitary Engineers developed a safety and quality standard for above-ground enclosures. It's known as ASSE 1060, and it addresses all 5 of these concerns: freeze protection to 30 below, vertical load strength of 100 pounds per square foot, full flow drainage capacity, and with respect to accessibility, we sought and obtained from OSHA this written confirmation that our enclosures do not qualify as confined space hazards, subject to its many safety constraints. Within a few years, the IPC adopted the new standard, and that code simply reads, outdoor enclosures for backflow prevention devices shall comply with ASSE 1060. And despite adoption, ASSE 1060 is poorly understood by purveyors and rarely mentioned in specifications. Given our earlier fascination with the topic of liability, we've added that parameter as an additional consideration here. Doug Krieger is an attorney that specializes in cross-connection control litigation and advocacy. He was quoted in Plumbing Standards magazine, initially in 2009, and then it was rerun again last year. He said an outdoor above-ground backflow preventer installation may be the best way to 1. Reduce the owner's exposure to damage caused by flooding and the corresponding water contamination caused by a cross-connection, and 2. Reduce the legal liability of the design engineers, the installers, and the certified testers whose professional actions in part may have otherwise caused the flooding harm. The water industry has a nationally accepted design criteria in ASSE's 1060 to protect these installations. It's a win-win-win insurance policy. Speaking of insurance policies, Ricky Roach is the fire marshal of Waycross, Georgia. He recently got a letter from the city's casualty and liability carrier, Zurich North America, stating that commencing July 1, 2014, noncompliance with the provisions set forth in NFPA Code 13.8.1.4 released in November 2013, just a few months ago, regarding fire sprinkler installation will result in premium rate increases and/or cancellation. So you understand what this code refers to. It's weatherproofing all outdoor backflow preventers. Obviously a good thing for safety cover in general. But understand this. Insurance companies are creating the urgency now rather than municipalities. They've determined that there are some practices out there that are expensive and they want them stopped. As far as we know, Zurich NA is the first insurer to step into this breach, but rest assured all other carriers will follow in short order. We predict that this preoccupation with backflow preventers won't stop there either. It can only be a matter of time before risk raters get their hands on the DeBoard article I showed you earlier and use it to systematically reduce risk by uprating buildings with indoor RPZs. So what's happening around the country that might help us understand where all this is going? We've been watching Northern Illinois. It all started last fall with the city of Elgin. On October 24th, 2012, they amended their domestic water service requirements as follows. All new commercial and industrial construction, each domestic water service shall have a reduced pressure principal backflow preventer assembly installed directly after the city water meter. Then they repeated that verbiage to encompass all remodels of commercial and industrial building as well. What's meaningful about this is that there is now in Elgin no longer a high hazard threshold. All commercial and industrial projects get an RPZ on the domestic line, period. A few months later, the city of Chicago amended their guidelines as follows. All new combination service shall require a domestic meter and an approved backflow device with bypass meter for the fire system. If these services are in excess of 50 feet for 2 inches or 100 feet for 3 inches, they must meet the above requirement and shall require the backflow preventer to be installed in an above-ground heated enclosure located as close to the property line as physically possible. What's meaningful about this is not that it's changing a hazard level, but there are many cold weather cities in the United States that have rejected the idea that above-ground enclosure is a suitable freeze protection device. But here we have the city of Chicago, and even more importantly, Chicago Fire, stating that their preference is to have the backflow preventer near the front of the property line in an above-ground enclosure. Finally, a few months later, not to be outdone by Elgin, Naperville raised them one by amending their guidelines to require RPZs on all commercial and multi-residential new construction for all services, fire, irrigation, and domestic. So not only is there now no longer a hazard threshold in Naperville, there are no more double checks. Within our Atlanta watch list, Roswell, Georgia is an Atlanta suburb of 200,000 people in Fulton County. Because legacy methods die slowly, last summer they articulated a very smart middle ground position for getting backflow preventers out of harm's way. Recognizing that drain capacities for small-sized RPZs can be accommodated with a typical 4-inch drain system, they detailed 2 methods of RPZ placement, one indoors for small RPZs and one outdoors for larger sizes. The drawings for the indoor method explicitly address drain system requirements and force designers to reconcile the flood rate risks with specific drainage system capacities. And the outdoor method mandates an enclosure that is ASSE 1060 compliant. In the Mountain West, Denver, Colorado has long had the reputation of being a leader in infrastructure quality. In 2012 and in 2013, Denver Water, one of the nation's largest water purveyors, added specifications and drawings for above-ground backflow preventer enclosures to their standard details. They make specific recommendations about 3-inch and larger RPZs and even small double-check backflow preventers being deployed to above-ground enclosures. Finally, Central Ohio, Delaware. In the 2013 release of their Infrastructure Design Guide, they now mandate RPZs in outdoor enclosures on all commercial, industrial, and industrial water lines, domestic, fire, and irrigation. Changes like these are literally occurring all over the country. So here's the first hard question. Why a vault? Ever? There are testing and maintenance access issues, as well as safety issues with vaults. Flooded vaults violate the International Plumbing Code, and if that vault deployed double check ever has to change, RPZ retrofits are expensive and they're usually not very pretty. They're also occurring more often today because a new tenant often means a new hazard level, and where such a provision might not have been enforced in years past, there's a lot of evidence that it will be enforced moving forward. And even if the use doesn't change, purveyors are lowering the hazard threshold to cover uses or drop the high hazard requirement altogether, as we saw in Elgin and Naperville, Illinois. Over time, because all of these unknowns, we will conclude that the vault installation method is the most expensive installation method possible. Okay, so now for the second hard question. Why place RPZs inside? Ever? Unless extraordinary drain capacity systems are employed, larger devices bring significant property damage risk to any project. And given that reality, insurance premium rate riders are close behind. Yeah, you can make the case for why smaller RPZs can be adequately provided for from a drain capacity point of view inside, but then scope becomes a moving target. On smaller pipe sizes, the MEP will take care of the backflow preventer. On larger ones, the civil will take care of it. Well, what's the pipe size threshold? And what if the pipe diameter changes during design? Is it worth it just so you can put a small RPZ inside? So as promised, let's look at what's happening in your neck of the woods. These are the cities in our Ohio watch list, the 6 fastest growing cities by total population since 2000. As you know, Ohio's water safety and distribution guidelines are governed by the Ohio EPA and then implemented by the Ohio Plumbing Code. So as a starting baseline, let's see what these codes collectively contribute to the backflow at the service connection question for domestic, fire, and irrigation lines. So let's ask this question. Is a backflow preventer absolutely positively required at the service connection? Green means yes. Yellow means it depends, and red means no, a backflow preventer is not required at the service connection. As you can see, before any local codes are added, backflow preventers are required for all fire lines and all separately tapped irrigation lines. The domestic service, however, may or may not require a backflow preventer depending on the degree of hazard implemented by the user. It's important to understand where the state level stops and the local districts begin. So here we go. So in looking at how local codes impact this absolutely positively have to have a backflow preventer question, we'll focus on the 6 areas identified earlier. As you can see, all these jurisdictions have added local code provisions that mandate at least a double-check backflow preventer at the service connection for domestic lines. Beyond that, the new Delaware code mentioned earlier goes further and mandates not only a backflow preventer assembly on all lines, but in fact RPZs on all lines. While not indicated here, and as previously mentioned, these new containment devices must also be outdoors in above ground enclosures as close to the service connection as possible. Next, we add the so-called tenant provision recently adopted by the City of Columbus, and because Dublin, Grove City, and Hilliard are all stipulating to the Columbus guidelines, they're all included here by default. What it means is that unless you can warrant that the user is a low hazard owner-operator of the property, and as such the building will never be subject to hazard changes in the future, as would be possible with any tenant-occupied building, then the builder is required to place an RPZ backflow preventer on the domestic water line at the service connection. This essentially eliminates any high hazard threshold for all but a few properties. Of course, when you add the conventional high hazard threshold requirement that we've all become familiar with, Marysville joins the other jurisdictions in the demand for an RPZ on the domestic line. Fire lines must utilize an RPZ anytime flame retardants or antifreeze are incorporated into the system. If I've been able to persuade you that the coming best practice for containment backflow prevention is RPZs all the time, then there are only two questions to deal with regarding the jurisdiction you're working in. First, are RPZs allowed in any situation where you, the designer, deems it appropriate? And the answer is uniformly yes. Anytime you specify an RPZ, these local water districts are happy to accommodate you. After all, RPZ protection is superior to double check protection. The other question is, are ASSE 1060 heated enclosures allowed for any backflow preventer on any line? Well, the answer to this question is a little murky in central Ohio, all except for Delaware, which we've already covered. So let's look at the other two jurisdictions, beginning with Marysville. I'm not saying we would never use an outdoor heated setting. Our preference is to have it inside the structure. Should a situation arise that would be more conducive to install an outdoor setting, we would consider all options at that time. Scott Shepard is a bright young guy, newly minted in an old, well-established system. And as he seeks to find the proper approach between city needs and designer accommodation, not only is a little time going to have to pass, but other districts are likely to have to step up and take the lead. So let's look at Columbus. And by default, Dublin, Grove City, and Hilliard. These guys demonstrate a profound willingness to accommodate. But there is often a problem because the legacy method in Columbus is to install the water meter indoors. Given the fact that the meter is indoors and the fact that they want the backflow preventer to be installed immediately after the meter, placing the backflow preventer indoors is simply practical from both a water security and plumbing efficiency point of view. It's probably fair to say that when this practice began, a lot fewer RPZs were being installed on domestic lines. But my, how things have changed. I met with some of Columbus's water people on Monday of this week, and trust me when I tell you that they are not interested in forcing you to take on any liability risk that is not necessary. They've stated that they will accept outdoor enclosures for backflow preventers, but as the saying goes, the devil is in the details, right? After speaking with their plans review folks and the meter maintenance team, it's clear that it's a more or less case-by-case approval process, which I know is the kind of thing that gives you guys ulcers. I want to encourage you, though, that there is great interest in a much more clearly defined solution that includes containment backflow prevention out near the service connection. Now, this discussion was long underway before I got here. Don't think we started it. Hopefully, our experience with developing standard details for other cities, including Roswell, Charlotte, Chicago, and others, might be helpful. But with us or without us, I believe they are committed to a more clearly defined solution. I've been invited back by Pat Crumley, the city's backflow compliance director, in a few weeks to visit with the engineering staff, and I'll keep updated with your permission with any progress we're able to make. It's very important to us that we make you aware of the significant strengths that differentiate the safety cover enclosure from its competitors and its freeze protection. Freeze protection quality and reliability is critical for areas like Central Ohio. Our heater system is patented and unduplicated. We alone utilize a floor heater that's actually mounted to the slab. Moreover, only the safety cover heater is UL listed for damp and wet conditions. Every other enclosure uses a non-UL listed wall heater. In addition to heating the enclosure air volume, this element heats the vertical pipe runs down 16 inches. And because heat dissipates vertically, we've doubled the R rating in the roof of all our models from the required R9 to R18. Together, these improvements save 20% on energy usage compared to the competitor and reduce thermostat-driven heat-on intervals by 25%. So make no mistake that the safety cover is the superior product with respect to freeze protection. As I mentioned, I hope to return in a few weeks to Columbus Water's engineering team and eventually offer some ideas that are based on practices while developed elsewhere are still getting really excellent results. One of the ideas we will be suggesting is based on a recent detail we completed for the City of Chicago, which they are extremely pleased with this far. It's an above-ground combination enclosure that houses the meter and the domestic and fire line backflow assemblies. Of course, if placing the fire line backflow preventer within this enclosure is not preferred, then it can be dealt with separately. But from what we've learned thus far, it's the combination meter and backflow preventer solution with its proximity to the right-of-way that improves their tactical capability in the field. Now, these things don't materialize overnight, but with other details available now that have been in place long enough to get feedback from the various interests, progress should be measurable soon. Finally, I want to let you know about a great little tool. Click on our website. At the very top, there's a button that reads, "Click here to size your backflow preventer enclosure." There, you'll see a simple 7-site calculator that allows you to specify the exact enclosure needed for your job. We'll isolate what we need here. We'll pick an RP, let's say 6 inches. We'll use Wilkins, which is a 375. We'll use OS&Y as the valve shutoff. Yes, we'd like a strainer. And because it's the state of New York, we know we'll need a 30-inch clearance from the midline of the device. So there we go. And click Search. Now, because I've been so specific with my parameters, it will be equally specific with its selection. If I'd have left some of the fields blank, I would have more choices here. But as it is, my project will need model 600T AL. I click on that link and get all of the specifications after the submittal sheet, which is first. There you go. Then the specifications to follow. Then return to the solution page. Click View Backflow. There I see the enclosure with the named backflow preventer inside the drawing in both an elevation view and a plan view. These are also PDF format so that I can drop them right into my drawings. Thank you for the opportunity to present this information. If you have any questions or comments, please email me at randy@safetycover.com or phone me at 800-245-6333.